Okay, good afternoon, everyone. I'm Per Stenström. I'm a professor in the Computer Science and Engineering department. And as an early Christmas present, I have the pleasure to introduce our very distinguished speaker, Professor Michael Jordan of University of California, Berkeley. So Michael Jordan is the Pehong Chen Distinguished Professor in Electrical Engineering and the Computer Science department. And not only that, he's also professor in the Statistics department at UC Berkeley. He's a member of the American Academy of Arts and Science, and he has received many fellowships, many very prestigious awards. The list is long of achievements. So it's indeed a great pleasure to have you here, Michael. And we just learned that you are actually in Italy now, so that's great. I'm happy to give the floor to you and listen to this very interesting presentation. Thank you.
All right. Thank you very much, Per. Thank you both to Per and to Frida for introducing and inviting me. And thanks to all the audience for joining us this afternoon. I have in the past often gone to Sweden. I really love going there, and it's a pleasure to be there, at least virtually. Also, I wanted to mention that I had received a prize this year for the Ulf Grunander Prize, and I don't normally make a big deal out of prizes and awards, but that was a pleasure. Ulf Grunander, as many of you hopefully know, was a leading figure in Swedish mathematics and statistics for a long time, a colleague of Kramer and a big presence who eventually went to Brown, but had a role in Sweden for many, many years. So I'm going to be talking about machine learning, and AI. Really, the terminology is now often being used to refer to the same entity as machine learning, and I want to talk a little bit about what these terms mean first of all before we get going on concepts, new ideas. So hopefully you all recognize John McCarthy on this slide. AI was coined by McCarthy in the 1950s, and it was really an aspiration, almost philosophical, that computers existed. They had software and they had hardware that seemed a little bit like the mind and the brain. Would it be possible to embody a mind and a brain on a computer? And is that conceivable? And that's, of course, exciting possibility and worth considering. I think that aspiration is still very much alive. It's still very, very exciting, but I don't believe it's happened. I don't believe we have thought on the computer yet. And we're not even quite sure yet, still to this day, what that would mean. And it's worth working on, but it's not the only thing that's worth working on. And it's not actually the thing that has changed technology and changed human life so much over the last few decades. So I think of it as still an aspiration, not really an engineering field. In the meantime, as I wrote about it in an article that's referenced at the bottom, it actually was published in Harvard Data Science Review right now. Which I think is a wonderful new publication you may want to look at if you haven't seen before. In the meantime, intelligence augmentation is sometimes used for the idea that computers augment human intelligence. They make us smarter in some ways. Even a search engine can be viewed that way. It's made all of us smarter. We have information at our fingertips and so on. And things like natural language translation, in some sense, augments our ability to communicate and so on and so forth. And I think this is really much more what's happened over the last few decades than AI. Computers have changed our lives by expanding our capabilities and possibilities in many, many ways. And in this, the computer itself is not very intelligent. So it's definitely not the classical AI dream. A search engine is arguably not intelligent in any way. It indexes information, but in a useful way. In the meantime, I think there's actually something else which is emerging, which is very exciting, and it really is kind of a form of AI, but it's not the classical McCarthy form. Let's call it intelligent infrastructure, just for to have an acronym. So it's kind of like the Internet of Things, but the Internet of Things was limited to kind of the networking problem. How do you get things on the internet? But if all those things are devices which have sensory data and they help make decisions locally, and all of that information converges in some sense, and if it's planetary scale, then we have an entity, which is a kind of a decision-making pattern recognition network that's planetary scale for problems that matter to human beings, like commerce or medicine or transportation and so on and so forth. So I think this is what actually is being worked on in many, many companies, and is what we often are referring to when we're talking about AI. But because it's so far away from the idea of putting a human thought in a single computer and interacting with that entity, I do think it's worth distinguishing. Moreover, in the meantime, there's also this entity called machine learning, which is somehow a little bit orthogonal to those developments I just alluded to. And I view machine learning as not a new field per se. It's really based on inference and computation. It's based on ideas from statistics that are hundreds of years old. It's based on ideas from computation that are decades old. But it has had a big impact in the real world. And that's what engineering fields do. So just to be clear on what that impact has been, already in the 1990s, machine learning was a terminology, and a company like Amazon built back-end systems that had many tens of thousands of computers that were linked, and they collected large amounts of data, and they modeled that data with the technology of the day, which was usually random forests. And they were able to do things like fraud detection, so you could do e-commerce to bring the fraud rate down to a small number. But even more importantly, supply chain management. If you're selling 1 billion products actually now to hundreds of millions of people, then managing the supply chain of where all the parts for those products are coming from and how they're coming together at the right place at the right time is a monumental task. And it was done by, by data analysis and by computing, by machine learning. So this is kind of the beginnings of a $1 billion industry in that era where machine learning was a critical ingredient. I think the second generation was, a decade later, when it was realized that a lot of the data that had been collected was about humans. It wasn't just about supply chains. And humans had preferences and desires, and there was transactional behavior. So modeling that and making recommendation systems, that was another very, very important, really $1 billion industry to help people with commerce and connect people in a commercial sense. So I think that the back end was the same machine learning algorithms and the same compute platforms that had been used for the first generation, just had gotten better, and eventually it was called the cloud. That's where the cloud came from. The third generation is the one that everyone is now talking about so much, or even let's call it hyping. Let's call it the pattern recognition era. It's neural networks and deep learning and all that. It's the same technology. It's the same large amounts of compute, large amounts of data, and the same kind of algorithms, random forest, deep neural nets, and the same kind of things that have been used 20 years before. So the scale had changed, but somehow qualitatively not much has changed. What I think happened is that the data was now not just about supply chains and about commerce. It was about things like speech and vision and people's pattern recognition abilities. And because you could now mimic people in that regard, it seemed like it was AI. It seemed like we'd arrived at the era of AI. And so, of course, the newspapers called it that, and a lot of people did. It was not AI in any deep sense, in the McCarthy sense. There's no semantics in the natural language translation behind the Google translator to this day. There's no understanding, and there's no modeling of the world, and so on. So it's really far from AI, but it has a commercial impact. That said, I would argue it's not nearly the same commercial impact as the first generation and the second generation. We haven't seen the $1 billion industry yet for AlphaGo and for vision systems yet. And it'll emerge. In the meantime, again, I think something else is emerging, which is even more interesting than a computer doing pattern recognition and acting like a human. That's this notion of networks and coupled decisions that are planetary scale. And let's call these now markets, because they're not just about data and prediction. They're about decision making in the context of interacting agents. That's a market. And we have to think about the algorithmic consequences now of putting these kind of market systems together with learning systems. And that is what leads to new academic problems and new problems for industry. There really isn't yet a field that devotes itself to learning and markets together. All right, so let me just say this kind of philosophical point one more way, which is that every few decades, or maybe every century, you see a new engineering field emerging in human life. And so take chemical engineering as an example. So it emerged in the 40s and 50s. Before that, there was not a field called chemical engineering. There was not even a real world entity of chemical engineering. There was chemistry, and there was quantum mechanics and fluid flow. And so there was a deep understanding at that point of what happened in a laboratory when you put two test tubes together and you made something. But the idea that you could build a factory and do that kind of thing at scale with huge flows and and products coming out the other end and so on, that was a dream. And people started to build factories, and sometimes they would work and sometimes they would not. Sometimes they would explode, and sometimes they would just not work. The product wouldn't be made, and so on. So a new field had to emerge to support that activity, and it was called chemical engineering. It's not just engineering. It's quote unquote. It's a mathematical discipline of its own. There's new thermodynamics principles that were needed to be discovered, new aspects of new PDEs devoted to that field, and so on and so forth. So I know less about electrical engineering, the history, but I suspect it's very similar. Before it emerged, at the end of the 19th century, you had electromagnetism, you had Maxwell's equations and optics and so on. So you had a deep understanding of the underlying scientific phenomenon, but to bring electricity into people's homes and build circuits and bring power across the country, you needed new principles. And so electrical engineering is that field that emerged, and it's a mathematical field too. It's not just engineering. Ideas of impedance, ideas of circuit design, and so on had to be developed, and they were. So I think that's actually what's happening now, that we have the scientific ideas of inference from statistics, algorithms, computation from computer science, and principles from other fields like optimization, economics, increasingly. And those are the scientific ideas, but to build engineering and real-world systems, you need new ideas. And so that's what I think has been happening in the real world at places like Amazon or Alibaba or whatever. They've been building those systems. Uber builds a system that works in the real world with data and preferences and so on. But they don't really know what they're doing. And they're often building systems that have problems. Either they don't or they hurt people. And so we need a new field that addresses this. So I think that's actually what machine learning is. Machine learning is not a new field intellectually. It has very few brand new ideas that weren't present in statistics particularly, but it has this conceptual problem of trying to do real world engineering systems based on inference and data flows and computing, which is new. Okay, so if you buy that, let's think about what machine learning really has to tackle to be such an engineering field. Well, it does have to do pattern recognition. It has to look at the data and find patterns that are repeatable and useful, but it also has to make decisions based on those patterns. And decision-making is often viewed as the easy part, or it's not talked about as much, particularly by the people doing deep learning. Often they say, all you have to do is prediction and that's enough. And I'm going to very much strongly disagree with that point of view. And I'm going to talk about the decision-making side. Decision-making comes in when you talk about not just whether there's a cat in the image or something. It's about high-stake decisions, like whether you're going to have a medical operation or whether you should change the supply of some vaccine in one part of the world versus another, and really important life or death decisions. And it's about understanding decisions and having dialogue about them. It's about sequences. It's about multiple decisions. And particularly, it's about multiple decision makers and market mechanisms all being brought together. So that's what I want to talk about. So my outline is I'm going to say a little bit more about decision making and learning systems. Then I'm going to talk about bringing market ideas together with learning systems, and talk about bandits and some related topics. And the other topics we'll see how much time I have to be able to get to. I do want to say something about Ray at the end, which is our work at Berkeley on a distributed platform. So if you're more of a software person, I hope you'll find that interesting. It's kind of a distributed form of Python for this emerging engineering field. All right, so let's talk a little bit more about decision making. As I've alluded to, it's not just a simple thresholding of a neural network. That's a very impoverished idea of decision making. So let's think concretely about you're visiting your doctor next year, and your doctor more and more is going to measure a lot of things about your body. Not just your height and your weight, your blood pressure, but many other things. And maybe even measure your genome, sequence your genome. And so imagine that, they measure 100,000 variables about you. And imagine that someone has created a very large learning system, a neural network that has taken in all of the world's medical knowledge and been trained on that. So it's somehow a super medical system. And your data goes into that neural network. And now you look at the output of that system, it's making predictions about you. And maybe it makes a prediction that you're going to have a heart attack, within the next year. Now, what does that mean to make a prediction like that? Well, it means that some number came out of the system that was over some threshold. So suppose that the threshold was 0.7, and for you, the number comes out to be 0.701. So really, is that a decision? And the answer is obviously not. You're not going to trust that result. You're going to, first of all, you're going to ask about the error bar, the confidence interval. And you're going to ask, where did the data come from to support that confidence interval? Why is there uncertainty? Is it because it was a different machine being used for me and the people in the training data? Maybe the people in the training data were different from me in some way. It's relevant. Maybe you didn't know some facts about me, about my history, about my family. And you're going to start to have this dialogue with the doctor at that point, and try to unpack what the meaning of this result is. And in that dialogue, you're going to ask counterfactual questions, things like, what if I were to do something different? What if the world had been different? What would have happened? And now you start to see it was not, the neural network did not have all the world's medical knowledge in it. That's an impossible idea, because I'm remembering, as I'm having that dialogue, things that happened to me that didn't seem relevant. They were probably not gathered as data in the past, that become immediately relevant to this particular decision given the new data. So all of those issues start to be part of the decision, and the system should support that. It should look at other data, it should train things in a different way, and so on and so forth. And a system needs to support that. Now that's just for one decision, but we never just make one decision. Today I'm making multiple decisions at multiple timescales. They're linked in various ways. And I'm just one person. We're often making decisions in a network. Certainly the medical system is a network of linked decisions. If some treatment works for one person, that becomes known and is used for other people. And right now, that's all being done in a very ad hoc way. Some doctor writes an article that's maybe read by some other doctor, and so on. But we really want to be thinking about building networks to support that kind of thing. And now we have to think about decision making and accuracy and learning and errors across a network, and talk about things like false discovery rate instead of just classical precision, recall, and accuracy. Kind of the fraction of errors should be small across some collection. We want to talk about things over time, and I don't mean just over one day. That's kind of the classical neural net situation. You gather a lot of data today, you train a network, you make predictions, and you do that over again the next day. Real learning systems should work over decades. They should adjust over time, and their provenance of the data will start to matter at that point. The data will often be older and stale. How much does that matter? You have to take that into account. So database concepts will need to be needed to support this kind of thing, just like they did for the banking industry. Now, it's never just decisions of a bunch of people. It's decisions when there's scarcity and competition. People may want to all do the same thing, go down the same road on the network of roads, and congestion becomes a problem. So how do you manage those kind of things? That's where you start to need market mechanisms to be interacting with the learning system. All right, so I could go on, but hopefully you see the decision making is not just make predictions and threshold, and then you're done. All right, so let's take a little thought experiment, classical recommendation systems. So, a recommendation system, we all know what it is. If you go and buy some books, say at Amazon, it'll start to recognize the pattern of what kind of books you seem to like, and it'll recommend other books like that by comparing you to other people who've been buying books. This has become a commodity. It's really a core part of the pattern recognition part of machine learning. It's kind of a matrix factorization problem or a clustering problem, and many people have worked on it. And it's so much of a commodity that you can download software and just try it out and try to build a business around a recommendation system. And that has happened a lot, and problems have arisen. And so the problems, one of the big problems is when there's competition. So in the simpler, older systems, there was no competition. If I recommend the same movie to lots of people, suppose that my service is recommending movies, and suddenly, millions of people are using my service. And I recommend to everybody some movies based on their past history. Well, there's a good chance I'll recommend the same movie to to 10,000 people or 100,000 people, just because it's a popular movie and whatever. There's no constraint on that. And that's not a problem, because I can copy the bits as much as I want and stream them to everybody in parallel. And so there's no scarcity. And this is the mindset, I think, of a lot of of the computer science world that built recommendation systems. There's no scarcity. You just do it independently for everybody. And that also worked for books, you know, which Amazon did, because you could print on demand. If you had a huge number of requests for some book, you could print it within a day. And so that's still the mindset. But now imagine recommending restaurants to people. So, you know, I arrive in Stockholm and I don't speak Swedish, and I'm by myself. It's 6 p.m. I want to have dinner. I don't want to look browse, you know, a bunch of reviews. I don't want to go to some site that tries to convince me of things. I want to just participate in a market at that point. I would like to kind of push a button on my cell phone and say, geolocate me, use some relevant facts about my history, about what kind of food I like, about what my price point is, and transmit that information to the other side of the market, the restaurants, and let their apps look at the possible clients, which include me, and start to make offers and bids. And this could all be done electronically. At the end of it, I get a bid from maybe one or more restaurants, and I look at the offer and I decide, oh, that's close by. I like that food. Yes, I'll go there. So that's not a recommendation system, because a recommendation system would just take in information about me. It would put it into a big box, and the box would output a list of restaurants. And if that were to happen for a small number of people, no problem. But if now everyone in Stockholm was using the app, it could easily recommend the same restaurant to 2,000 people, and everybody might go there, and we'd create a line, and we wouldn't all be able to get in. And so how do you fix that? You could say, well, it's just a load balancing problem. The app will decide who gets to be in there based on some criterion. And I think this is what Silicon Valley and IT companies often do. They think they're going to figure out how to build the system, and they know enough about people to make the decisions for people. So they know, you know, the Facebook knows your browsing history, knows your friends. So it's going to figure out which restaurant you really would prefer to go to, and it'll give you that one. It'll give the other restaurant to somebody else. And I hope you see how ridiculous that is. There's no way Facebook could or should know about our particular desires. And in fact, those desires will often come in the moment. I will be walking on the street and I will have a thought of some kind that makes me want to go to a certain kind of restaurant. And so that's more like how we participate in markets. We kind of have a thought, and we would be willing to pay a little bit more in some auction sense for some outcome. And we would change our mind depending on the flow around us and depending on whoever else is participating in the overall market. So building a system that does that instead of just doing Facebook or Netflix style recommendation, that's a major intellectual challenge and an interesting business opportunity. Same thing happens when you recommend streets to drivers. You know, if you're trying to get people from their house to the airport very quickly, if there was no one else on the roads, you'd know what the fastest path would be, and you'd offer that to them. But as soon as many people start to use such an app, you'll send everybody down the same streets, and you'll create congestion. You'll make the streets slower. And so now again, you have to decide who gets to go down which streets, and you can't decide that. It has to be part of an overall market where people are making bids based on their particular momentary interests. So the alternative to creating just a learning-based system that decides everything and does pattern recognition is to create a market, decision-making on both sides of a market. So for example, diners and restaurants both get to decide what kind of offers they want to make. Streets and drivers are on the two sides of a market, and they get connected up by the market, and so on. So this is very much like microeconomics, matching markets, game theory. But those people in economics rarely talked about data in the sense of unknown preferences. They assumed that you knew the preferences on both sides of the market, and then they built matching mechanisms and so on. When you don't have those preferences, you could start to run an auction and start to learn about preferences. But what if I have 10,000 restaurants or 100,000 books? I can't have an auction at that scale. I can't know the preferences a priori. I have to use the aggregate collective experience of lots of people and bring that into the market. So that's the machine learning meets markets perspective. I should mention David Blackwell. I got to know David Blackwell. He was a mathematician, statistician, probabilist, and so on at Berkeley. And he worked on problems like this. He was working in statistics, economics, and algorithms. And in the 1950s, 60s, 70s was thinking this kind of way. And it wasn't only him, Ken Arrow, Bellman, and others. But that kind of unified perspective kind of disappeared. Computer science went its way, statistics went its way, electrical engineering went its way, and they kind of separated. And so what I'm partly arguing is they should come back together. And that's sometimes called data science, the bringing back together those fields. But what I think has been missing in the data science discussions, it also needs to include economics, because it has to have this game and mechanism flavor for things to work in the real world. All right, so in fact, this perspective is not entirely new either. Markets are algorithms, right? They have rules and they have behaviors and they can be analyzed, and they have nice properties. They're adaptive, they're robust, they're scalable. They're pretty far away from the classical AI perspective. This is not what McCarthy was talking about, and Newell and Simon and all. But markets already exhibit intelligent behavior. You know, the system that brings food into Stockholm every day is an overall set of decisions that makes local decisions that lead to globally reasonable behavior, that food arrives in the city. So it's intelligent, it's adaptive, it's robust, and so on. So we need to bring those ideas into contact with more of the data and intelligence ideas. All right, so if you think this way, there's lots of new problems to work on. You know, multi-way markets where you have to explore to learn preferences, recommendation, information sharing, auctions in which preferences learn, and so on and so forth. So the overall goal then is start to build real-world systems that are learning-based, but they're also market-based, and they're stabilized over long stretches of time, and they're transparent, and they're healthy, and they're fair, and all those kind of things that we would like to have our systems be. You need economics and statistics principles to build such systems. All right, so let me now turn to being very concrete. So I'm going to talk about a particular one of our projects. We've been doing many projects with this flavor, market ideas meet learning. And let me tell you about one is one of my favorite ones that was done with Lydia Liu and Horia Mania, students with me at Berkeley. And so let's talk about Bandits. So Bandits is kind of one of the core learning problems. It's my favorite learning problem, even more than supervised learning. And so you have an agent trying to make a decision between a number of actions, and you don't have labels that tell you which action is best. So you have to try out the actions. You maybe pull that arm and you get a reward. And there's an unknown reward distribution behind each action. So you learn a little bit about the reward you're going to get by trying that arm. And you then try the second arm perhaps, and you keep going. Over time, you'll start to model and build an idea of which arm is best. But as you're doing that, you'd also like to get rewards. You don't want to just wait till the future to get rewards. So there's this trade-off between exploring and learning which arm is good, and exploiting, which is to get rewards as you're learning. So there's been beautiful work on managing that trade-off. Probably the most famous algorithm is called the UCB, upper confidence bound algorithm. And it basically just uses core statistical ideas. It uses a confidence bound on the reward distribution. It doesn't model the whole distribution. It just uses a confidence bound. And instead of taking the middle of the confidence bound or something, it takes the upper confidence bound. So the upper confidence bound, for example, right there, could be high for one of two reasons. First of all, the whole reward distribution could be shifted to the right and be very good. So you want to pull that arm because you'll get rewards. Or you could have high uncertainty for that arm, and therefore the upper confidence bound is high. If you have higher uncertainty, you also want to pull the arm so you can learn more about the arm. And so for two reasons, you'd like to use the upper confidence bound idea. And so it does manage the trade-off. And you can now prove theorems about this algorithm that picks the upper confidence bound, and you will prove that it learns, that it has a regret, which is logarithmic in the number of trials. Regret is how much reward you lost relative to an agent who knew the best arm from the very beginning. Okay, so that regret, if that grows linearly, you're not learning at all. Just you're doing bad at every step. If it grows sublinearly, square root n or log n, you are learning. And so this algorithm learns. So we're going to put that together with matching markets, which is the concept from microeconomics, game theory, that we want to bring together with learning. So a matching market, you all know what it is. There's buyers and sellers. They're assumed to have known preferences for the other side of the market. And given the preferences on both sides of the market, you find a matching, which in some sense makes everybody relatively happy with the match that they've received. And there's a famous algorithm due to Gale and Shapley that finds such a matching in polynomial time. Okay, so I think you can see where I'm going. What if you don't know the preferences a priori? All right, what if you have to explore the choices on the other side of the market to find what your preferences are? So you can't do a matching from the very beginning. You have to both explore, learn, and match as you go. So in particular, suppose we have two competing agents here, and they start pulling the arms and learning about the arms, maybe using UCB. That's all fine, but what if they both pick the same arm at some point? Well, at that moment, you have to decide what you're going to do. And so we are trying to model scarcity and competition. So our assumption is that only one of them will get a reward at that point, and the other gets no reward at all. Okay. So who gets the reward? Well, again, this is a two-way market. So on the arms side of the market, the arms have preferences back on the agents. And those are unknown, and they may be even stochastic, and they need to be learned as well. So what has happened here is that the human learned that maybe the human likes arm 2, but the bear seems to like arm 2 as well. And when the bear picks the arm, the bear gets the arm more often than the human. And having learned that, now you're less likely to pick arm 2 in the future. And that's maybe bad because you liked arm 2. But now you have to explore more and see if you can find another arm, which is also something you like. So you can see that the exploration-exploitation trade-off becomes more interesting in this setting, and you need to try to quantify that. Okay, so we've defined now a notion of a bandit market. You get rewards when you pull things, and there's competition. And now we have to define a notion of regret, so we can start to do the theory of bandit markets. And so our notion of regret's a pretty natural one. It says, if you knew the preferences a priori, which you don't, but if some oracle knew them, and the oracle ran the Gale-Shapley algorithm on those preferences, they would get a certain matching. And the question is, how well do you do relative to that? So that's our notion of regret. We call it the stable regret. And the question is now, can you achieve a sublinear regret relative to the stable regret for some algorithm? All right, and so here's a particular algorithm we've analyzed. We've analyzed some others too, but we call this Gale-Shapley upper confidence bound, and it's very natural. Every agent maintains a upper confidence bound on all of the arms. And at each step, they send their upper confidence bound value to the matching algorithm, say Gale-Shapley. It finds a match based on those uncertain values. And then that tells the arms the agents which arms they can pull. They pull them and they get the reward and they update their upper confidence bound. Okay, so that's our algorithm here. And we analyzed that, and we were able to, in fact, achieve a logarithmic regret. So not only does this learn in this market, it learns fast. Moreover, there's a term in the denominator, delta squared, which reflects the reward gap between the agents. So that actually captures mathematically the competition. And in fact, you have to explore more, and you have a worse regret when there are other agents who have rewards that are similar to yours in the population of agents. Moreover, at the bottom of that slide, we were actually able to prove that this algorithm is incentive compatible, meaning that if everyone else is playing Gale-Shapley UCB, you are incentivized to play that algorithm. If you move away from it, you will do worse. Anyway, so this is, I think, the beginning of a little field here of learning meets game theory in a kind of very clear learning sense. It's really a learning algorithm. You run an algorithm and it collects data and it changes. But you're bringing in market principles to shape that learning experience. All right, so having worked on UCB for a while and recognized its power in decision-making, that it could be applied to things like markets, we said, well, let's also apply to some other decision-making problems where there's more than one decision. And so the simple one next step was to work on now reinforcement learning, which is just the bandit problem where you have not just one decision, you have a sequence of decisions. So you make a sequence of decisions and there's some underlying state. And at the end, you may get a reward, or even during the sequence of actions, you get some rewards. All right, so this is work with Qi-Zhen, Zheyan Ayanzhu, and Sebastian Bubeck. And I won't want to get into details too much here, but many of you will know what reinforcement learning is. It has also been a little bit overhyped, but let's not get into that too much. But anyway, it's the bandit problem with Markov decision process behind it. It has states. So given state X1, you make an action choice, maybe with a bandit type algorithm, you get a reward. And then the state changes and you do this again and so on. And you accumulate rewards over time. All right, so in this setting, you have a couple of choices about how to approach this problem. The model-free reinforcement learning paradigm kind of is more like the bandit idea. You just try out some actions, you see what rewards you get, and you adjust the policy, which chooses actions incrementally in some way based on your experience. The other approach, however, is to model the transitions and then based on the model of the transitions, run an algorithm that's like dynamic programming to find the optimal choice of actions. So that's called model-based RL. And then there's a huge debate, both among the empirical people who tend to be dominant these days, and the theoretical people about which is best. And roughly speaking, in practice, they both can be made to work really, really well. In theory, it seemed like the model-based paradigm had a strong advantage. But the problem was that the theory people were not using things like UCB. They were actually not solving the exploration-exploitation trade-off. They were just worried about the temporal properties, the Markovian properties of these models, and proving their theorems based on that. All right, so we decided that we would try to go back at this problem again. It's an old problem, but bringing UCB into contact with Q-learning. So again, I'm not going to get into details, but if you know about reinforcement, you'll know that Q-learning is a way to learn value functions given a certain state and given a certain action, what's the value. So it's kind of like a reward distribution for each state, if you will. And this little update here in line 2 updates the Q values based on the reward you've gotten. And all we've done here is to add a UCB upper penalty. That's B sub T in red there. It's the UCB bonus, and you can see how we set it at the bottom there. So instead of just taking the mean rewards and modeling them, we're modeling the upper confidence bounds on the rewards. It's kind of a simple algorithmic change, but now you have to do the theory of that, and that's quite challenging. Anyway, we were able to do that theory, and I want to show you some results now. This is one page, just summarizing the whole literature really for now kind of a decade. All of the work on, there's a lot of work on the model-based paradigm. That's at the top of the slide there. And you can see that the regret that people were able to prove was square root in T, where T is the number of trials that you've gone through. Okay, so the amount of time that's passed. So square in T is good. It's not logarithmic, but it's square root. That's still learning. You're sublinear. Okay, if you go down to the next 2 lines in the model-free paradigm, Q-learning was studied, and you can see that its regret was not square root of T. It was T, or T to the 4/5, so worse. But here there was not exploration being incorporated in a reasonable way, in a sophisticated way. What was done was epsilon greedy was being used. Epsilon greedy is just where you randomly occasionally try a different action than what you think is the best. And that's not as smart as UCB, right? So anyway, the new results are that if you put UCB in there, you also get square root of T regret. That's the 2 shaded regions there. So that's our new results. You can see that there's a lower bound. So we are very close. In fact, we match the lower bound with respect to T. Okay. Okay, so there's lots more you can do with UCB type penalties and so on. And I'm going to not talk about some of the further work we've done there, but there's a lot of it, our group and others, bringing together more of a formal exploration-exploitation trade-off with more sophisticated decision-making than just bandits. Okay, the next little vignette I'd like to talk about is now when we're talking about decision-making, I want to talk about not just one decision like in a bandit, nor just a sequence of decisions like in reinforcement learning. I'm going to talk about now groups of decisions, bags of decisions, maybe being made by a single person over a period of time in their lives, or maybe being made by a group of people like in a company or a country or something like that. Okay, so we're going to talk about continuous decision-making made by groups of people. And this is work with Tiana Zernich and Aditya Ramdas at Berkeley with me. Okay, so decision-making classically in statistics and other fields was thought of as a one-time thing. You know, the Neyman Pearson paradigm is you had a hypothesis test and you collected some data and you made it a yes/no decision, and that you're done. Okay. Then people started to think more about things like multiple decision-making and Bonferroni ideas and so on, where you would maybe have not just one hypothesis, you'd have a set of hypotheses. And now you would penalize yourself more. Your alpha value, your threshold for making a decision would be smaller so that your overall rate over the entire set of decisions could be controlled, even though you're making multiple decisions. The problem with those approaches is that as you get more and more decisions, your alpha gets smaller and smaller and smaller so that you control the overall error. It's just a union bound. And so eventually, if you're going to make huge numbers of decisions, you have to, you have no power. You're not allowed to have a large alpha value, so therefore you rarely make a real discovery. You rarely reject the null hypothesis. So you have to stop making decisions in this paradigm. And that seems strange because, you know, we don't stop making decisions in our lifetime. Even as we get older, we still can make some good decisions, and we feel that we have control over all the overall error rate that we're incurring. We're not just kind of dying as decision makers. Right? So is it possible to do this in a statistically sound way, to actually continue to have anytime online asynchronous decision making, whereas you still have a control over the error rate? All right, so what does that mean? First of all, well, it means that imagine my boss or some oracle comes in and stops me at some moment and says, how many discoveries have you made today? Or how many decisions have you made today? And I say, well, I've made, 1,000 decisions today. And of those decisions, I've made, like 300 discoveries, meaning I rejected the null hypothesis. I said that something was happening that was interesting. And the boss will say, well, that's great, 300 discoveries. Well, what fraction of those are false discoveries? That you made a false positive. And I'll say, well, only 10. And at any given moment, the boss should be able to stop me and say, what fraction of the discoveries you made up until now in your entire history are false discoveries? And I would like to be able to say that only 5% or 1% of my discoveries at any point in my life are false discoveries. So is that possible? All right, that's certainly a worthy goal. And the answer is it's possible. But you need economics ideas here. You need to think about errors now, not just as kind of a threshold, but as a form of wealth. And you can accumulate wealth over time, and you can use your wealth to make investments for future decisions. All right, so I'm gonna not get into a lot of details here, but I wanna say a little bit more about this multiple decision perspective, because it's not as widely known as it should be. So imagine I have some true nulls. Suppose I'm doing 9 decisions here, okay? And the gray ones are ones that I should not make a discovery. There's nothing to discover. Whereas the red ones, I should make a discovery. And suppose I run some algorithm and I make 4 discoveries. 2 of them are false discoveries and 2 are true discoveries. So my fraction, my rate is 1/2, which is not particularly good. That rate is called the false discovery proportion, and you can define that over any stretch of time or even over a group of people. Its expectation is called the false discovery rate, and this is a very famous now quantity in statistics, which is for like 2 decades now. And why is it important? Well, imagine you're like an industry, Amazon or Google or whatever, and you're running A/B tests. So it's very common to run, tens of thousands of A/B tests every day. It costs some money. Maybe you're trying to change the website or something. And usually most of the changes you make are not going to make an effect. You should not, they're null. You should not make a discovery. So let's imagine you did 10,000 A/B tests and 9,900 were actually in null. There was nothing to discover, but in 100 cases, there was something to discover. They're non-null. And now you a researcher, you develop some neural network or some fancy classification algorithm, and you trained it on data so that its type 1 error rate was 0.05, meaning when something was null, you did not make a discovery most of the time, 95% of the time. And suppose you in fact applied it to those data, that means that 0.05 times 9,900 is equal to 495. You made 495 false discoveries out of this 10,000. And again, that's very good error rate, right? Small, less than 0.05. And imagine your neural network also has a high power. When you're supposed to make a discovery, it does make a discovery. So of those 100, its power is 0.8. You multiply by 0.8, you get 80 true discoveries out of 100. Again, that's a very good fraction. So this is the kind of numbers you'll often see, very high sensitivity, specificity, whatever language you like. I'm using this, but I'm doing this at scale. And the question is, am I really doing the right thing here? And the answer is no. Because if you look at the total number of discoveries you made today, it's 575. And so if your boss says, well, how many discoveries did you make? You say 575, because the boss doesn't care about the non-discoveries, right? Those are not something you're going to act on, like change the website or something. So of the 575 discoveries, how many of them were false? Actually 495. So almost all of your discoveries are actually false. And if you were to implement those changes on the website, you would lose a lot of money. And after a few months go by, you would discover that and your boss would probably fire you. All right, so this is a huge, huge problem, and you can solve the problem. And the way you solve it is you develop one of these kind of economic perspectives on this. There is a perspective due to Benjamin Hochberg, which is a batch method. You collect a lot of p-values you sort them, and then you threshold based on the sorted p-values, but that's a batch procedure. You can't do that in an anytime way during your life. All right, so long story short, we and some others have worked on this. We have a paper called SAFFRON, and it does control on an anytime basis. And the core idea is that the FDP is a ratio, and you can make ratios small by making the numerator small or making the denominator large. The classical error rates are not a ratio where both of the quantities are random variables. And here, both of them are random variables. And so you can control the numerator or the denominator. So roughly speaking, I have a little picture to suggest this. Whenever you make a discovery, the denominator got bigger, and therefore I give you a little alpha value that you can use as wealth, and you can use that to invest for future decisions. And there's kind of a little martingale argument behind this. All right, so anyway, I just want to let you know that that's possible. It's a simple algorithm. We've put it in our own software for making decisions, and we hope that many other people will as well. I've decided based on my time here that I'm going to skip this next little section, but this is a little more for the mathematicians in the audience. You know, Bandit algorithms are running over time and they're accumulating information. And can you develop a general mathematical framework that says you accumulate information fast enough that your decision-making process has logarithmic regret? And the answer is we've been able to find ways to do that using Langevin dynamics, you know, stochastic differential equations based on Langevin theory, and been able to develop a general theory of you know, fast learning when you're making decisions in the Bandit setting in continuous bandits. So let me just skip over that for want of time. I do want to get to the last little part here. So if you're interested in this, we have some papers where we're doing this theory. All right, let's skip over all that. Okay, so my last few minutes, I'd like to be a software engineer. And so I believe that if you're going to have impact with these kind of ideas, it's not enough just to prove theorems and show empirical results. You have to actually build systems that people really use. So Ray is a platform that aims to put all of this asynchronous long-term decision-making in a large-scale platform that anyone can use, that can run not just on one computer, but can run on the cloud. It can run on 100,000 computers just as easily as it can run on one computer. And you can see all my colleagues there at Berkeley. We have a whole project for 3 years now on developing Ray. So Ray, one way of thinking about it is that the current machine learning ecosystem has many little capabilities, training, serving, streaming, hyperparameter search, and so on. And different groups, you know, often in academia, sometimes in companies, have been developing these capabilities as different standalone pieces of software. You know, for training, you have distributed training and serving and so on. The way we've been thinking about this is what you really need is one distributed system that handles the entire the distributed part of the problem, that worries about the scheduling and the storage issues. And then all of these capabilities are built as libraries on top of that. So we want an API and a language that allows you to express distributed machine learning that's, again, asynchronous and it's decision oriented. Another way to think about this is that you know, the success of a modern language such as Python is based in part on the fact that it does both functional programming and object-oriented programming. It kind of blends them and allows you to make use of those in the same paradigm. And programmers find that very, very appealing. And it's a simple language that does that. When people went to the cloud and they went to programming the cloud, things like MapReduce became the popular paradigm, that you would run, you know, your software on 100,000 computers. You really couldn't do object-oriented programming then because you had to worry about how the objects were coherent with each other. And when computers are going up and down, that became hard. So it was functional programming again. And so MapReduce, that's functional programming. And so Hadoop and then Spark and that entire paradigm was functional. Very important, but limited. If you go now to modern neural nets and, you know, AlphaGo and systems like this, you have to have objects. You have to have state being stored over long stretches of time. You know, a neural net is full of state. So you cannot just have a functional programming paradigm. And so that has got to be overcome. So Ray is both functional and object-oriented. It has tasks and actors. And that's critical for this modern paradigm. So you could think about Ray as really just distributed Python. In fact, its first API is written in Python. And I'm going to show you an example here. This is some code that someone else wrote. I think this is a researcher at OpenAI. They were doing hyperparameter search for a neural network. And so this is their code, and it's running on a single computer. But you really want to have this be, multi-threaded. It really should run on a huge number, 10,000 computers, so that you can find hyperparameters quickly. So they said, can we use Ray for this? And we said, yeah, all you got to do is, this is just Python, right? Just add a few lines of code that make it a Ray program. And you can see the red things that have been added here. They're very, very, very simple. Okay, and this immediately just added that, and it ran on, as many computers as you wanted to. So this has now been 3 years. We have a broad range of scalable algorithms that are running on top of this, and things running below this. It's optimization oriented and decision theoretic oriented and statistics oriented. Okay. Here is the underlying architecture just briefly. It is more complex than some others because it's doing a lot. It's actually managing objects across a network. So it has object manager and stores. It has scheduling being done as well, and it manages all of that. This is an open source project. There are hundreds of people now worldwide working on it, and you can certainly see and contribute to this project. But it definitely is biting the bullet of having some complexity under the hood so that the API can be extremely simple, really just distributed Python. Here are some of the third-party libraries that have been built on top of this, just to say. So you'll recognize some of these. Like we said earlier, we thought that if we built a single framework that we would have easy to build libraries on top of it, and that has been the case. So let me just mention one last application, and then I'm going to end here. The company Alibaba in China has developed Alipay, which a billion Chinese are using, and they had to model the interaction of people with this website, and not website, with this app, and that was sort of a day of featurization and training and model serving. They then spent about a year updating their software and were able to bring it down to 1 day instead of from 1 day to an hour, and that was a big money maker for them. And then they participated in Ray. So in fact, this is the first Chinese company doing open source development, and Ray was able to bring it down to 5 minutes, much quicker than the engineering effort that went into a year of changing the existing legacy system. Spark is the world's most widely used data analysis platform, and you can see the growth of Spark since 2015. Ray is matching Spark's growth at this point. We're pretty proud of that. Our lab developed Spark, and we think Ray is even going to be a bigger win. Contributors worldwide as of September was nearly 400. Companies that are actually using Ray in production include Ant Group, Amazon, Goldman Sachs, Intel, and so on. And just to conclude, so Ray is distributed Python. You can download it there from a GitHub address and be contributing to it as well. So let me finish with just returning to a slide I had up earlier. Machine learning is an exciting field. It's having a big impact, but it has been limited to pattern recognition. And I think that's created confusion, it's created hype, and it's created a lack of awareness of the research opportunities that really interact with many other fields, mostly including economics in this field, but many others too, optimization, and operative research, and so on and so forth. And those problems often lie on the decision-making side of the field. So I'm going to finish there. I think I've left some time, 5 minutes or so, for questions, and I would love to have questions if there are any. Thank you.
Thank you so much, Michael, for this wonderful talk. I did just get thrown out of the Zoom meeting a second ago, and now I'm back. So this has meant that I can't actually see the questions that were written in the chat anymore. So I do ask that my co-host, Devlet Debashli, help me out reading questions from the chat. Please go ahead, Devlet.
Okay, so I can take them in reverse order. So here's somebody asking about the potential. What's your view on the potential of transformer models to being applied beyond language tasks? Value of data, can we train general purpose models also for decision making?
So I don't work on transformer models. That's the pattern recognition problem. So my talk was not about that at all. Let me just pass on that. I mean, I don't think that the neural network people have not really focused on decision making, frankly. And I think that that is a problem. So false discovery rate, as I alluded to, it's just a very natural way to measure the accuracy of any system, and the deep learning people have not been using false discovery. They've been using accuracy, precision recall, and so on. And when you go beyond these language tasks, which are all on the internet, you know, it's all software. It's not interacting with the real world, right? It's not making real world decisions about you know, allocation problems or people's preferences or decisions or interactions among decisions and all that. Then you know, it's not high stakes. I mean, if a language model says the wrong word in a sentence, that's not life or death. All right. You know, and so those models are really amazing. They're absolutely amazing, but they still make lots of errors, and it's not clear how to control them, and it's not clear the consequences of those. So I really do want to, you know, I love the transformer model. I love the pattern recognition thing, but it's not everything, and that's not what my talk was about.
Would there be a component in your market-based mechanisms to, if there is an interaction via dialogue and so on, natural language dialogue to make decisions?
But it's so dialogue, real dialogue between you and me right now, and between any two humans is based on a state, and it's based on an understanding of what happened yesterday. It's based on a shared model of the world. And these language systems, like the transform models, are not doing any of that. They're not building up any state. They're not having any semantics. They're not modeling the interaction, the social and physical relationships in the world that are being talked about. Okay, so they're very, very far away from the kind of things I'm trying to talk about. They are just mapping strings to strings. They're taking a Swedish string and mapping that to an English string based on those strings having occurred in some sense together in the past. All right, that's not understanding. And so it's very, very far away from this kind of being able to have a real dialogue. A real dialogue with someone is that we really understand each other and we ask questions that are relevant to what we've been building up as a shared understanding. And they're not doing that at all.
Okay, that's a big research agenda that they should address at some point, I guess. So here's another question that maybe is closer to something that you talked about. So Jakob Schneidman asks, would a cooperative bandit be fundamentally different? For example, if you have two agents playing, I mean, he takes the example of Tinder, they pull the same lever on Tinder.
Yeah, great question. Thank you. Fundamentally different and very interesting. In fact, there's been some work on different kinds of congestion channels in the EE literature. So if you, in a wireless system, if two people try to go down the same channel, neither one of them gets a reward. You create a congestion and nobody can get a signal through. That's a different model. It's very interesting. That's a competition. Cooperation leads you into cooperative game theory, and it leads into collusion and kind of trying to, you know, decide how to help each other. It leads to information sharing. And so all kinds of mechanism design and literature is devoted to that. And we're absolutely interested in studying those kind of things in the learning paradigm. We just wanted to, first of all, get at the scarcity and competition issue, but we think that cooperation is even more interesting. And in fact, if you think about bringing recommendation systems here to bear, you know, if I'm exploring restaurants in Shanghai and Frederick is exploring restaurants too, we should share the information and learn from each other and cooperate to explore the space of restaurants, especially if we seem to learn that we have the same taste and so on and so forth. So you really see learning and cooperation and game theory really starting to interact in a very, very interesting way.
So I remember from before we had a question in the chat about the traffic directions example that you used to illustrate the market problem. So a comment was made that often, you know, Google Maps and competitors will use congestion to sort of estimate the time that it would take to go somewhere, and so your recommendation might change. Does this solve the problem, or is it fundamentally different?
Yeah, it's fundamentally different because they created a problem, which is the congestion, right? And then they looked at it and said, "Oh, we now have congestion. Let's back away from it." So it's like a feedback control system, right? What we really want is a feed-forward system that didn't create the congestion in the first place, right? So yeah, no, they're aware of it. And I by the way, when I say kind of bad things about Google or whatever, I love, they're my friends, and they're working on all these things, and they're aware of all these things. But I just think that the reporting coming out of the PR and the media and all of reporting on that they've solved the world's problems and they have the mechanism, the machinery to do that, and they don't, and they're aware of that, right? And so in fact, you know, yes, the Google Maps creates congestion and they're aware of it, but they don't have a good mechanism to solve it in their mind and also in mine, which is really, it should be the case that if I'm going to the airport and a lot of people are going to the airport, that somehow an avatar, my cell phone kind of says, I'm going to the airport. And the system in some ways sets up a bidding process of some kind, that it sort of it comes back to me and says, well, a lot of people want to go down the road. How much of a hurry are you today? And you have some money. Or are you willing to spend some money on going a little faster today? And I say, well, no, actually today I'm not in a hurry at all. And I'd love to actually see a nice, I'd like to go up on the mountains and see something different today. So I'll save my money for a later day. And the system then gives the road to somebody else who's really in a hurry that day for a good reason, maybe. If you don't have that kind of mechanism, you will not solve the problem, right? That's how humans interact when there's scarcity. There has to be something. And I don't want to be in an auction every time I have to make a decision, but that's where computers can come in. The computer will be an avatar for me and it'll run the auction on my behalf. And the computer and I will interact. I will just say, the computer will say, hey, are you in a hurry today? And I'll say no, or maybe it'll know that.
Thank you. Devlet, do you have another question from the audience?
Okay, let me take another one. So since you were talking about connection of economics and game theory into AI and learning, here's a question asking if things from behavioral economics like prospect theory and so on are relevant or interesting.
Absolutely, 100%, yes. So first of all, let me just say I'm not the first person to talk about these things. All those people are very much talking about these things. I think that they're welcoming the idea that these learning ideas that we have are going to be coming to their field more and more, and this engineering perspective on it. Prospect theory is often saying things about, well, classical notions of preference and utility are kind of broken, that humans don't really quite use those, and we have some other ways to think about it. And as learning people, we should absolutely be aware of those, and our model should be taking those into account. Just when you talk about biases in learning, the mechanism we use should be aware of those biases, and it should be either helping them or hindering them or being aware of them at least. And so if you're really trying to have humans be happy, you have to be happy on their terms, not on just the mathematical terms. So yeah, I think there'll be a real flowering in this is going to be a several decade thing, just like chemical engineering, right? It wasn't just a few years, it was decades. And electrical engineering, same thing here. So, all the economists, legal scholars will be needed here, psychologists, but interacting in a language that is really kind of a computing and inference language, right? That allows us to be, formal and build real systems.
So a short question on the last part of your talk. So you shared this curve where you showed the growth of Spark and Ray was catching up. So what's the relationship now between Ray and Spark, or is there one? I mean, is one going to supersede the other?
All right. So I'm not supposed to say this, but I think that Spark is surpassed by Ray. Now that's not true in any real sense. Spark is the world's most widely used platform, and that means that every company in the world is using it in production. And so it's a batch paradigm. It takes in a very big batch of data, and it analyzes it with a really wonderful library, and then it deploys, right? And that's fine for some problems, but that has natural limitations. Many situations you cannot wait for the batch, right? And you want streaming capability, and you want asynchronous streaming, right? And so that's what we're aware of. Spark, we said the problem is it's block synchronous, and that's just not working for things like if you wanted to implement AlphaGo, which is doing a tree search, right? Well, some branches of the tree take a long time, and other branches don't take a long time, but Spark makes everything take the same amount of time because it's block synchronous. So how could we move away from that? And we said, well, the only way to do it is to really embrace asynchrony. And so really, Ray is exactly like Spark or MapReduce, but embraces asynchrony. When a process finishes, the system immediately is aware of that, and it starts up a new process. So it's more of a tree and not a block synchronous paradigm. That's really all it is at some level. But then the machinery to implement that was the headache that we had to face with Ray. So I think in the conceptual space, it just surpasses Spark because you really do have to have asynchrony is better than synchrony. But in terms of the company, Databricks is worth several $1 billion now because Spark is a real entity in the real world. That's not going to go away. Just like IBM never went away, there will always be Spark. But I do think that Ray is the more exciting current project.
So a follow-up question on that. We had Bill Daly from NVIDIA as a guest a few weeks ago. Who was talking about hardware and AI and how they interact. Is Ray built for the current generation of hardware? Should we change hardware to work more better with that kind of system? What's your take on that?
That's a great question. So I don't know. I'm not really a hardware guy. I mean, Dave Patterson, others are my friends, and they have their own perspectives on that. And Bill Daly obviously is someone who could give you an expert's opinion on that. I think that NVIDIA and GPUs was kind of a magical thing, that is, these big graphics-oriented matrix operations were perfectly fit for pattern recognition of the layered neural network kind. And so people have run with that and exploited that, and that really helped set that off. But just as I was alluding to, if you're doing things like tree search or Monte Carlo search or this kind of decision making over groups, then GPUs are no help there. It's not the right paradigm for that. Ray tries to integrate these things, right? Our actors can be a neural net, and the actor can be based on GPUs. And in fact, Ray allows you to to use GPUs and CPUs as a mix. All right, so it has the pattern recognition side as part of it, but then it adds all this other machinery, which is asynchronous and decision oriented and having state over large amounts of time. And I'm not a hardware guy, but I can't imagine that will not spawn new hardware requirements and ways of thinking about it, thinking about where the temporal bottlenecks are, where you have to have kind of provenance information, where you have to worry about security issues in new ways and all that. So I'm absolutely sure, in 20 years, we'll look back and say there was a new paradigm that was invented. And I don't know what it is, but I'm super excited to start to watch it evolve. It's not going to be just layers and matrices and pattern recognition, though. Like I say, I hope that came away from my talk. There is something else, and definitely hardware people should be thinking about what that something else is. Doing this in real time is kind of part of the perspective here, right? We're trying to make real-time decisions at planetary scale. And that's definitely not just crunching big matrices of numbers.
So we are very happy that Per is listening to this. So maybe he can, give us some hardware perspectives at Chalmers. So Frederick, what about your question about, you had a question about healthcare.
There we go. So yeah, Mike, you used healthcare as an example of a high-stakes decision before, where we don't believe pattern recognition to be enough, and I completely agree with you, naturally. However, the market perspective that you brought up in the talk today, do you think that sort of fits the healthcare the setting, or should we think in other ways?
Yeah, that's one I wish we had a beer and we had a couple of hours so we could sort of chat about it, because it's absolutely complex and interesting. And let me just sort of say the naive perspective is that markets solve everything, and I'm a capitalist, and that's just obviously wrong. Markets have lots of problems and they create lots of headaches and all that. But they are a force. And if you'll permit me, just, again, the metaphor, suppose you're developing civil engineering as a field, right? And you're trying to build bridges and buildings and all that. And this is now several hundred years ago. And someone says, well, how are we going to incorporate gravity into our field, right? Gravity is a bad thing, right? Because gravity pulls people towards the earth, and people die because they fall off of buildings and off bridges. We should not use gravity. It's a bad thing. Let's build civil engineering without gravity. We'll have pulleys and all kinds of mechanisms. We don't need gravity because it's a bad thing. And you could have done that, but of course that's stupid. The better thing to do is to exploit gravity and to control it and to regulate it and all that. Same thing, markets are an extremely powerful force in human existence, and not just humans, I think even bacteria. And so you have to understand it, exploit it, control it, and build it into the rest of the things you're doing. All right. So I wouldn't want kind of crass, stupid notions of markets to go into something like healthcare, where the rich get better healthcare than the poor or something like that. We can't do that. But we have to recognize there's scarcity in healthcare of some kinds. We can't do the same test on everything. We can't, even with the vaccine, we had to kind of, pick a number of people to actually be tested on. And we had to have some people in the control branch and some in the treatment. And there's scarcity about how we roll out the vaccine, all that stuff. And you have to have mechanisms to confront that scarcity and to make it as equal and fair as possible. That doesn't mean the richer get it and not. It means that you have a mechanism design that has socially useful outcomes as the design. And then you try to achieve that by incentivizing people to behave in ways that make it all kind of work out. And remember also that markets are not just about money and about bidding and auctions. Matching markets, for example, the kidney exchange is the most famous example of a matching market, where people, if you have two functioning kidneys, you can give one to somebody else. And you'd love to give it to your brother if your brother is about ready to lose their second kidney, but maybe your blood types don't match. So instead you have to give it to somebody else who gives it to somebody else who gives it to your brother. And so that's a computer science or economics problem, and there's no money involved. You're not selling your kidney, but it saved, millions of lives. And so that kind of perspective brought in to say, think about the COVID response, right? It's been very ad hoc. People tried out different things in different places. There was different flows of information. There was, You know, I mean, it's in some ways amazingly effective after a year that we have a vaccine, but it's also, we're going to lose, you know, millions of people by very, very ad hoc, bad decision-making all along the way. And computer scientists and statisticians could have helped, you know, 10 years ago designing a better way to do that system. You know, also I spent, part of my perspective came from spending a lot of time in China over the last decade and watching the rollout, not just of cell phones, but of Alipay. And people in China could pick up their cell phone and hold it in front of a QR code and pay and transact. And old people, young people, everyone is doing it. And that gave a fluidity to the society that was very, very healthy for China. And it hadn't happened in the West yet. And they are now doing that with their healthcare, right? One of the reasons that you have such low COVID in China is not just that it's a government with the military out in the streets. It's because the cell phone usage and the QR codes and all that allow them to actually recognize what's happening much more quickly and to keep people away from outbreaks and so on and so forth. You know, so I'm not sure if I'm answering your question. I just wanted to sort of say, to me, yes, healthcare is one of the mother of all problems. Climate maybe being the other. And we've done it in such ad hoc ways with doctors writing pieces of information on pieces of paper, with data gathered 10 years ago still being used without any error bars on that, with the database provenance ideas not being used, et cetera, et cetera. Our field has just not kind of grappled with it. And so, so yeah, a good message in my talk is that Mike Jordan doesn't know how to solve that problem, but he thinks that it should be, for young people in the audience, it should be one of the main things they're trying to focus on and work towards. It'll take a while though.
Thank you, thank
Per,
you.
you want to get in?
I think you're muted, Pat.
Yes, I am. No, I agree with Mike that, I mean, what's happening in computer architecture, it's a really hot topic today to understand how we should build efficient machines for future machine learning problems. And it's true, GPUs are very good at, you know, SIMD execution, but there's more to it that is needed. So this is an excellent topic and I'm very interested in it myself.
So Mike, what about a follow-up to you just talked about all the great things they managed to do in China, but what about the flip side there with, you know, that's the other flip side that everybody talks about these days, the surveillance and the points system to credit system to its citizens and so on?
Yeah, no, absolutely. First of all, my computer vision colleagues who are kind of responsible for the algorithms that are allowed to do surveillance, most of them don't want to work on face recognition or surveillance. They never wanted to work on it. They felt it was just not the kind of problem that would be helpful for society. You know, that said, someone was going to work on it and it was going to be possible to do, you know, face recognition and surveillance. And I think that really is more, it's just as much a technical problem as a legal problem and a societal problem and a dialogue problem about how these things are getting used. You know, all of us are using credit cards all the time, and that information is flowing into a system that knows everything about us from the point of view of all of our transactions. And so we have to accept whether that's good or bad. It gives us some fluidity in the world. We can more easily do certain kind of things. But there's a trade-off on that. And so you have to express that trade-off well, have dialogue about it. Open societies have to decide, well, you know, is it good that people know, like I'm in Italy right now, if I get on the train, should there be a message to me saying, hey, someone on the train has got COVID? Well, how do they know? Well, because, you know, some privacy was invaded. But is that good or bad? Well, that feels like to me a dialogue should be had about that, right? And we're sort of having that dialogue in awkward ways. You know, some government body will make some regulation, then people will fight it. But somehow we need to get to where we can actually talk about those things as the real trade-offs. What benefits do people get? How do you protect people when they don't want to get something? And you know, anyway, this is part of, to me, the several decade process of making this thing roll out. Let me just add another point of view, which is that, you know, 150 or 200 years ago, there were not big cities because there hadn't been the Industrial Revolution. So most people would live in villages. I'm sure that's true in Sweden, and I'm sure that's true in most countries in the world. And in a village, you had very little privacy, right? You had, everyone knew about you. Your doors were open and your life was open. And, you know, and so this idea that you can live without anyone knowing about you in a city, that's a modern invention. And it has some advantages, but it has some severe disadvantages. In the village, because everyone knew about you, they would help you if you had trouble, and they would look out for each other. And so, helping build our society where we can actually know things about each other, but do it in ways that are not invasive, but are actually helpful when it's wanted. Those are, really the major challenges, not just for us as technologists, but for everybody. Anyway, I don't have anything to say about the Chinese government. They have other problems there to kind of work towards democracy, hopefully, so that they can have these dialogues in an open and fair way too. But in the context of all the dialogue about China in the West, China is viewed as just aggressive and steals ideas and does, locks up people and all that. If you spent time in China in the last 10 years and you see the young people, embracing entrepreneurship, learning new ideas, learning about the West, walking around with their cell phones, interacting with each other and with the world, you'll recognize that, our kind of a perspective, markets, open source, idea flow has had a big, huge impact on China, and they've contributed to it. They've built these systems that are very, very open that, for example, do loans. Alipay, because people pay with a cell phone, you learn about their payment trajectory. You can validate whether they're likely to pay off a loan, and you can make loans to them. And that's what Ant Group did. So 1 billion people are getting microloans in China now. And the government, of course, is trying to regulate that more, and that's a big debate. But arguably, for 1 billion people who never had money before in their life to be able to get a small loan so they can, prepare for the holidays or whatever, is arguably a good thing for society. And China was ahead in that. So, these dialogues, I think, are often a little too focused on, caricatures. The Chinese do surveillance. Surveillance is machine learning, and it's more subtle and more rich than just that.
So do you agree with Kai-Fu Lee that China is ahead of the US now in the AI?
No,
space?
no. First of all, I don't think it means anything. Think about chemical engineering. Who was ahead of anyone else? Really, the answer is everybody did chemical engineering. Every country did it. They had factories and they did it in different ways. And they did it in different ways so that they could trade with each other, right? And they found advantages that were natural in their own country. They did it in a different way, and then they were able to trade. AI or machine learning, whatever you want to call it, computer science is so broad that one country cannot dominate it. It's just impossible. So each country does it in a different way, and then they find ways to take advantage of what they did that was different. Also, the engineering talent is the main thing for this. It's not algorithms. These are simple algorithms. This is gradient descent. This is hardware which is available everywhere. The data, you collect your own data. It's really about the engineering talent and the will to build that, and that's going to be solving each country's slightly different problems. You don't dominate with the technology. This is not what that's about. All right, and in fact, Sweden, will find a way to dominate in some part of it, just like they did with shipping, right? Sweden's dominated shipping, well, for there's historical reasons. And why did they do that? Well, good reasons. But that doesn't mean that no one else did shipping. Yeah, again, I think that our dialogue in the newspapers and all is really missing a lot of these points. It's, that there's a possibility of dominating AI. China's moving fast in AI. Oh my God, China's going to dominate AI. It's just completely silly.
So we have a question also from Morteza in the chat about active learning, and I'll try and add some context there. So, the way that most of us learn about machine learning for the first time is that we are given a data set and we learn some regression or a classifier or something like that. And then that's that. The data came once and we looked at it. But now that, ML software is deployed much more in practice, we do have the option to collect data again and update our model and so on. Do you think that this is something that is undervalued in terms of research, or do you think that this has a particular impact in the settings that you have been talking about today? Can you talk a little bit about active paradigms?
Yeah, no, I can. I've worked on it. It's certainly implicit in what I was saying. It just didn't come out explicitly. I tend to be I'm a computer scientist, but I'm also very much a statistician. And in statistics, active learning is always done. It's just, it's called experimental design, right? You would never gather data without thinking about how to gather the data, and you would actively gather data that you would hope would answer your question. And you might do that by literally measuring error bars and trying to make them smaller by gathering more data where you needed it the most. So that's a whole field. And it's now called active learning and machine learning. And as usual, the first people to use that terminology thought they were discovering something new. Their students came along and said, oh, but this has already been talked about. And they went and read the older literature, and they got new ideas and they pushed it forward. And that's what happened with active learning. Bandits are active learning. I hope you could see that Bandit is a simple form of active learning. Bandits were discovered in the 40s and 50s in statistics, right? And then now everyone else has contributed to it. The other part of this is kind of control theory and closed loop thinking. If I make decisions, that's going to affect what happens next and all that. And so I'm going to actively try to steer that system, right? And so that's definitely part of the calculations here. If you're optimizing, you're not just optimizing to get a label, you're optimizing to get a desired outcome, which may take some while for it to be revealed. But also think about the game theoretic setting. If Frederick and I are engaged with each other, maybe competing, maybe cooperating in some kind of way, and I'm trying to figure out, what data to collect to win, to beat Frederick, or maybe to help him or whatever, I'm going to have to be aware of what data Frederick already has. And I also have to be aware of what actions he might take if I take certain actions. And if I'm aware of that, I might realize that some data is just not useful to me because he would never take that action. So I don't need to worry about that. And so I therefore don't even bother gathering that data. So that's exactly an active learning problem, but now in a game theoretic context, right? And Frederick also mentioned earlier, he works on causal inference. Well, causal inference is very much about deciding what matters. What data should you gather for the purpose of deciding something, right? And so, yes, that's a really good question. I'm glad you're asking it. But just to say, yes, it's throughout this kind of perspective that it's about closed loops and about the consequences of actions and about consequences including other people, and therefore data sets you might gather or might not gather.
Thank you. Devda, do we have other questions in the chat from before?
No, I think we're kind of running out, and we've gone way over our time. So we've had a great discussion, and I guess we could continue, but we are probably imposing on Michael now. So maybe we should start, unless Frederick, you can find some questions that are urgent.
We had a very quick question before, which was for the Bandit, the sort of what was it called? The matching Bandit setting. Is there a lower bound?
No, there's not a lower bound. Great research opportunity.
Okay, another one from the same discussion. Now that you brought it up, so you had this other algorithm, with reinforcement learning with the UCB that almost matched the lower bound. But how well does that work in practice?
It worked great in practice. Absolutely, yeah, it's been picked up by other people.
Nice, quick answer.
I mean, literally, the problem is in practice, people do reinforcement learning. They just implement Q-learning, and then they do all kinds of bells and whistles around it, put lots of computers at it, right? But then they say, well, we also have to do the exploration. So we'll just throw in epsilon greedy, meaning that you arrive at a certain state, the Q value tells you which is the best action. And you say, well, what's probably epsilon, I'll pick some other action. It's the ad hoc thing to do. And in the domains that people have been exploring these things in, which are mainly like, video games and, and Go, that's fine because it just takes a day longer or something. Right, but it's not fine because that's just in high dimensional problems. Just randomly choosing some other action is not going to work, and so UCB is a much more targeted way to figure out what to do next. And so yeah, absolutely, it's the right way to do it, or it's a right way to do it.
I suppose it's becoming increasingly less fine the more compute we throw at the problems too, big for other reasons, for environmental and energy reasons.
Yeah, that's right. No,
compute
computer data solves everything. That it was always wrong, but it just too many people sort of didn't say that it was not enough. It was, a lot of money is being spent, a lot of lives are being spent in doing that kind of thing too, and then not a lot of carbon is being created to do it. Whereas a lot more thinking is needed than just big iron and big data and all that.
Okay, Michael, thank you so much for your talk and for this wonderful discussion. We're going to end it here. Do you have any words you want to leave us with?
No, I just want to thank all of you. That was a very great discussion, wonderful questions, large audience, and an awkward time for all of us and everything. But I've really appreciated the COVID era that I can sit in a room in Italy and be connected to an interesting, really exciting group of people, half a world away, and get to know you a little bit, and then we'll meet in the future in some way. But that's a good, aspect, neighborhood feeling that we have now. So thank everyone for participating.
So maybe next time you're in Italy, Michael, you can hop over to Sweden physically. We can host you in person next time.
Yeah, absolutely. I'm looking forward to. I'm not retiring anytime soon. I'm still very energetic, but when I say the retired word for me, that means Europe, and that means indeed Sweden.
Sounds great. Okay, thank you so much for the last
All right,
time, and
thank you.
Many
goodbye for now.
thanks, Mike.